Welcome back, everyone. In this video, we're going to walk through the steps of hypothesis testing, and I think this will help you to understand it a lot better. So in this section, we're going to learn 4 steps of hypothesis testing. We're going to view an example of a hypothesis test, and we are going to complete successfully, I might add, a hypothesis test. So let's just say that research has shown that cognitive functioning declines as people age. But some research noted that in rats, antioxidants seem to reverse this decline. So the question is, could it benefit humans? So this is a research question. Can antioxidants reverse cognitive decline in humans? So this is a mythical research study, and we have an independent variable and a dependent variable. The independent variable is the daily dose of blueberries for 6 months. This is what we're manipulating. This is something that we're trying to see if it makes a difference. That's the independent variable. The dependent variable is a test of cognition with something called the Wisconsin card sort. So let's just say we have a mythical sample of 25 people. They are all adults over the age of 65. And what we do know about the population of adults over the age of 65 is that their mean score on the Wisconsin card sort is 80 and the standard deviation is 20. So this is all the information we need to get started with our hypothesis testing. So after 6 months, the test is going to be administered to measure cognitive functioning. And if the mean score is noticeably different in our sample than the score in the population, we're going to conclude that the supplement actually worked, that there was a treatment effect, that eating these blueberries did something wonderful in terms of cognition in older adults. That we can say if the mean score is noticeably different. If the mean is about the same, then we're going to conclude that the supplement doesn't appear to have worked. So we're going to have 4 different steps. The first thing we're going to do is begin with a hypothesis. We're going to set a criteria for making a decision. We're going to collect data and compute a test statistic, and we're going to make a decision. And these 4 steps we're going to be doing over and over again in the rest of this semester. So we're going to begin with a hypothesis. And in this course, we're going to be talking about 2 different types of hypotheses, the null hypothesis and the alternative hypothesis. So this slide talks about the null hypothesis. When we make a null hypothesis, we state that there is no treatment effect. We're hypothesizing that what we're going to see in our sample is not going to be any different than what's in the population. There's no difference between the population mean and sample mean. So think of null and no and 0 and nada all being the same. The null hypothesis says nothing to see here. So in the upper right-hand corner, I have some statistical notation for the null hypothesis, which is a capital H and a subscript 0, 0 null. And what we're saying with the null hypothesis is that the population mean is going to be equal to the sample mean. And sometimes we notate that with the mu equals the capital M for the population mean equals the sample mean. That's the null hypothesis. The alternative hypothesis, however, is kind of what we're more interested in as researchers. We usually want to see that there's a treatment effect or that there's a difference between the population mean and the sample mean. We want our treatments to be effective. And so we also can set up what we call an alternative hypothesis. And that says the population mean and the sample mean are not the same, that they are different. And if you look at the upper right-hand corner, you see the capital H and the subscript of 1. That is the symbol for the alternative hypothesis. And we can notate it by saying that the population is not equal to the sample. So we use that inequality sign between the mu and the capital M there to show the alternative hypothesis. So the next thing we're going to do is set a criteria for making a decision about those mean differences. So we're going to locate boundaries that separate high probability and low probability events if the null is true, if it is true that there is no difference between the sample mean and the population mean. So this is going to be something new that we're going to introduce. It's called level of significance, or the alpha level, and it's indicated by that strange looking A. We use this level of significance or alpha level to define the very unlikely sample outcomes if the null hypothesis is true. This is going to make more sense as we move on. But what I want you to know now is, by convention, alpha levels are 0.05, 0.01, and sometimes 0.001. And so what that means is 0.05 is a 5% chance of finding our outcome if the null hypothesis is true. 0.01 means a 1% chance of our sample mean if the null hypothesis is true. And then a 0.001 is actually 1 in 1,000. And that you'll see in statistical software. So we kind of decide what we're going to consider low probability events if the null is true. And sometimes we set it at 0.05, 0.01, or 0.001, but most likely 0.05. So this is an illustration that shows the distribution of sample means if the null hypothesis is true. Remember, this is that DSM that we talked about, all the possible sample means that could come from a population. So what I've done here is I've shaded in what I'm going to call extreme low probability values if the null hypothesis is true. So those shaded areas are where if we would find our mean there, we would be suspicious. We would say, this is very strange. It's so very unlikely that we would find a mean that is so much different than the population mean in these extreme areas. The unshaded area represents the sample means that are considered to be close to the null hypothesis. And I know that it doesn't seem close, but all that part in the middle we call high probability that the null hypothesis is true. They're close. The tails of the distribution are shaded, and again, they represent low probability outcomes if the null hypothesis is true, and the remainder represents that high probability if the null is true. I know I'm repeating myself a little bit here, but. So what I've done here is I've circled the extreme tail areas, and I've also indicated the z-score that's associated with these extreme areas of what we call 0.05 or 5%. When we say that something is significant at the 0.05 level, that corresponds to a z-score in a two-tailed test of negative 1.96 or positive 1.96. Any z-scores above 1.96 or below negative 1.96 we would consider to be very extreme. So we call this the critical region. We say that these are such low probability events that we are going to reject the null hypothesis. We're going to say, no, the mean of the population is not equal to the mean of the sample, that they are statistically significantly different. So that is what we're doing in this aspect of hypothesis testing. We're setting a critical region, and we're deciding that if our sample mean is found in one of these critical regions, we're going to say, nope, there's something else going on here. We're going to reject the null hypothesis. So let's review a little bit about what we've been discussing. We set the boundaries of the critical region first by determining the alpha level. We decide what area in the normal curve would we consider to be an area that would contain low probability outcomes if the null hypothesis is true. If it is true that the population mean is equal to the sample mean, what sample means would be so rare that we would have to reconsider the null hypothesis, in other words. So our alpha level is determined a priori, which just means ahead of time. This is an ethical consideration for researchers. We can't change our alpha level afterwards to make it work for our research. What we do is we predetermine our alpha level and then test using that alpha level. We use our unit normal table that will provide a precise z-score for us to find the probabilities of finding our sample mean. So z-scores define the boundaries of the critical region. So for example, I've been showing you a two-tailed test with an alpha level of 0.05. When we have that 0.05 or 5% in a two-tailed test, what we're actually doing is splitting up that 0.05 into both tails. And therefore, we have 0.025 in the left tail and 0.025 in the right tail, meaning 2.5% of the means are in the left tail and 2.5% of the means in the DSM are in the right tail. The unit normal table for z-score boundary at this 0.05 level is 1.96, meaning that z-scores for our sample mean above 1.96 would be considered a low probability event, not likely to happen, or a z-score below negative 1.96 in a two-tail test is also pretty unlikely, and we consider that to be a low probability event. So just to reiterate, z-scores greater than 1.96 are low probability, and when this happens, and I should add z-scores less than 1.96 are low probability as well, when that happens, we reject the null hypothesis. We say that the sample is different from the population, and it is likely the case that the independent variable is responsible for this difference. So we're going to end this section with just a quick learning check. When Ashley conducts research and determines that the results are highly unlikely to have been due to random chance, she can state that her findings are what? Well, statistically significant. So we've done the first two steps. In the next video, we're going to go through the last two steps of hypothesis testing.